Do you think it gets faster and faster or the same speed the whole time? Faster and faster is the correct answer. So it is definitely going to be a uniformly accelerated motion. Now we can do this with other objects too. I have a single word search piece of paper. Is this considered a heavy object? No, this would not be considered a heavy object. If I dropped the book and the paper at the same time, would they hit the ground at the same time? No, they would probably not. For example, no, not even close. This one almost ran into the next person over here. All right. Okay. Much heavier than this, right? So, I'm going to alter this without messing with its mass, right? It weighs a certain amount, right? It's a little flimsy. It weighs a certain amount. Have I changed the weight of this object? Has this mass changed at all? Now, book plus paper. That was the same. Book's heavier than paper. Same time. Why? This is our topic. So why? This heavy book, light paper, same time. Yes, Noah?
They both fall at the same rate.
They absolutely fell at the same rate. How do we explain why they might have fallen at the same rate? Corbin? Gravity is generally why they fall. And gravity is constant on Earth. And so that's the shortcut as I say it. So, my example here is if I put them on the moon, what's the main difference between the moon and here? The moon does have less gravity, but it doesn't have some gravity. Yes, it has some. It's less, but it has some. What is the main difference between dropping the paper and the book on the moon?
Slower.
Well, it would be slower, yes, because it's less gravity. What else would happen? It would not float at all. Why not? Not because of gravity. Yeah, the moon has no air. So there's no air on the moon. That's what caused my piece of paper to fall slow the first time. Because air was involved. So it floated on the air. The air is giving it a push. It's messing with the gravity because it's pushing on it. And because the paper was really light, the push was strong enough to mess with it. Now, with it very small and crumpled up, the push was really, really small. There wasn't a lot of room to push on it, so it pushed essentially none. And so the gravity won, it was the same on both sides. So they would fall at the same time. Short answer, because no air. So in as few words as I can say, is there's no air on the moon, and this was actually done, and maybe after lesson I'll show you the video of it. The problem is the video was shot on the moon in 1971. It kind of looks junky. But it was a video shot on the moon in 1971, which is impressive enough as it is. But it also showed a full-on feather and a hammer falling at the same rate. It's still pretty cool. So you can still see it. I'll pull it up at the end of the lesson. So the acceleration of a freely falling object is called acceleration due to a gravity field. Which is very, very fancy. The good news is that we will now call this exceptionally long description G. Little lowercase g is the acceleration due to a gravity field. So it's much better. Little g is what we're going to use. Now, on Earth, near the Earth's surface, and that counts for every deepest valley to the highest mountain. It's close enough until you get into actual orbit that starts messing with gravity. So the gravity field is G is equal to 9.81 meters per second squared. So that's 3 significant figures. So there's 3 significant figures in our gravity measurement. And we're just going to basically accept this as a fact as far as your calculations are concerned. This measurement is accurate to 3 significant digits. It does vary past those digits a lot, whether you're up high on a mountain or low on a valley near the sea level. For us and our problem solvings, we can replace any A in a formula with G if the motion is only falling. So if this object is only falling down and there's no like wings on it, there's no rocket on it, it doesn't have a motor of some kind. If it's just an object falling down, A is exactly G. Because that's all that happens. Because we generally ignore all the wind that would happen to it. Because generally we choose objects that are minimally affected by wind. Cannons, softballs, which we'll get to later. They basically are unaffected by wind enough to change the mass or to change the motion. It's essentially the same as not air. Okay, math time. A very small marble is dropped from a height of 9.31 meters above the floor. How fast will the marble reach the floor? Now remember, we're looking at hit the floor. Well, it hit the floor, it stopped moving. That's not really what we're looking for. We're looking at the split second right before it hit the ground. How fast was it going at its fastest moment before hitting the ground? So that's the kind of assumptions we're making in these questions, so they're not like an entire paragraph of me explaining things. We do a lot of assumptions in here. Okay, start the question the same way we do all of them. We go through and list all the numbers we have and give them a variable. The first number I see here is the 9.30. And so what value is that? It's a height, but for us, we're going to call it a displacement. 9.30. And I'm going to do something a little creative here. And I'm going to say this is negative 9.30. Why would I add the negative to this particular number? Yeah, the marble traveled down. It went down. Went down. So its displacement is 9.3 meters below its starting point, which is why I put it negative there. Next number in the question. Oh, there's not very many numbers in the question, is there? What other assumptions can I make from the question? No. Gravity exists, so A is equal to negative 9.81 meters per second squared. Why is the gravity negative? It goes down. Gravity goes down. So I want to be clear with a few things here. I got to get on my soapbox and say this is very important. The value of G isn't negative. G is 9.81. In our question, the direction of travel is down, and so you can assign it a negative value for this equation. G itself isn't a negative number because students come into it and they put G is negative and then you get a negative and it turns into a positive number because you're adding too many negatives altogether. But G isn't negative, it's traveling down. That's different. Any other assumptions we can make about our question? We need one more assumption. Corbin. We do not know the final velocity. That's our goal, right? Our goal is to find, stop leaning on this. Velocity final is the unknown of our question. We do not know the final velocity. Oscar. The initial velocity, what is it? It's 0. Why? No, not everything. Why in this question can you assume your initial velocity is 0? Dropped is the key word. It wasn't thrown, it wasn't launched, it wasn't catapulted or any other words that would inspire emotion at the beginning. It was let go. It was released. These kinds of not giving it a beginning speed words. So, unfortunately, that does turn physics a lot into a vocabulary lesson of like learning all of our words. So now we have enough to do math. Which of your formulas can you solve this for? So this is another good reminder. The formula we want is VF squared equals V naught squared plus 2AD. And the good news is that I want to find the velocity so I can throw my numbers in here. Good starting point. Velocity is 0. We don't need that term, so I just need the other numbers. So this is equal to 2 times A, in this case, is minus 9.81. And we're going to multiply it by my distance traveled, 9.30. This is great news. What do I see that's great news here in the math? Corbin. The negatives will cancel out, which is excellent news. Why is the negatives canceling out excellent news? Because it's positive. Why is a positive number really good news? I got to take the square root of this number in the next step. You cannot take the square root of a negative number. That does not exist. So, the good news is I get this number of 182.46, bunch of numbers. I'm not going to write them all down because I'm not finished. I want to take the square root of that number before I get my answer. So let me slide down a bit, pop it up on the screen so you guys can see what I'm doing here. And I get 13.5, I'll round it to, in meters per second down. It's my final velocity there. Next question is a brick falling off the roof of a building. It took 3.89 seconds to hit the ground. How tall was the building? So I only gave you one number, and we can solve this equation. So we'll start with the one number I know. It's the t is equal to 3.89 seconds. What else can I assume about this particular object? Tori. Gravity works. A is equal to minus 9.81 meters per second squared. What else can I assume? Yep, I can assume the initial velocity. It's 0. And I think that's all I need. D is what I'm looking for. That's all. What formula has T, A, V naught, and D, and nothing else? Noah.
D equals the initial velocity times time plus half of acceleration times time squared.
Is that one. D is equal to V naught T plus half A T squared. That's the formula we're looking for. And I'm going to try to solve for D. So this is good. That's great. It's already arranged the right way. What is the next thing I notice about this equation and why I like it so much? Your VO is 0. And so your first term disappears. This whole thing, that goes away from the V naught being 0. Your initial velocity is 0. So you can get rid of that. So you really only have half AT squared to work on. So we now have the displacement is equal to 0.5 multiplied by minus 9.81 multiplied by 3.89 squared. So now I just have a calculator problem. I can type this in to my calculator and get a number. It's going to be a negative 74.222 and so on. So that's what the number gives me. What best description can you give this number? What does this number mean to the question?
Distance it traveled down.
Yeah, it went 74 meters down. The brick's final position is 74 meters below where it started. Should I include the negative in my answer? No, because what does the question want? The height of the building, right? It doesn't ask about the position of the brick relative to its starting point. It's asking for how tall the building was. So we're going to use our context clues to say the building is to the right number of significant digits. Looks like I need 3, 74.2 meters tall. So that's the height of the building. 74.2 meters tall according to our measurements. We'll slide up and do our last question there. If you drop your pencil off your desk 1.1 meters off the floor, how long will it take to fall? This is the 8th time I haven't fixed that typo. So how long does it take to fall? This is a time measurement. So I want to figure out what is t. I know my displacement will be negative 1.1 meters. What else do I know about my question? Initial velocity is 0. And A is equal to gravity. So those are all the pieces. Which formula shall I use?
Same one as last time.
Same one as the last time. Because it is. But it's a little scarier this time. D is equal to V naught T plus half of a t squared. So that's my formula. You may notice that I told you you can't solve that for t. Because you don't know, well, most of you, some of you don't know the quadratic equation yet. And those of you that do know it do not want to use it because it sucks. So we can use our cancellation procedures. This is a special case where it will work out nicely. Because what is the first thing we did in the last question? We can cancel out our V naught t. So because we can do this first, because that goes away, we can now solve for t just fine. Because now we only have one t term and not two t terms. There's a lot of alliteration there in that sentence. So now we have to work with, oops, not that color. I want this color. Not d is equal to just half of a t squared. So now that's all we have here, and we can solve for t now. What do I have to do to solve for t, get this letter t all by itself? What should I get rid of?
The A.
I get rid of a, but I also want to get rid of that half there. That's ugly. How do I get rid of the half first? No. Times 2. So we're going to multiply both by 2. I'm going to do this the stepwise way so we get it all correct. So I get 2d equals a t squared. Then what? We're going to divide by a. So we get 2d divided by a equals t squared. Now we square root. And I get t is equal to the square root of 2d divided by a for the case where your initial velocity is 0, which is fine. But only when your initial velocity is 0 does this work. So, as far as ordering things goes, we have to deal with the 2 and the a. We could do the a before the 2, that's fine. But we have to do both of those before the square root step because we have to do our solving steps for reverse BEDMAS. So we have to do all the add subtract steps first, then the multiply and divide steps, then the exponent step. Remember, a square root is an exponent operation. So we have to go backwards through our BEDMAS when we're doing things in order. So we can't square root first. Now just numbers. We can go this, oops, sorry about that screen move there. back to a good layout. We're going to put 2 times 1.1 over minus 9.81, and then square root that number. We can get that right in our calculator. 0.47 or so? 0.4735, and so on. How many significant digits should I keep in this particular question? 2. So time is 0.47 seconds to the ground. So that's roughly how long it takes to drop your pencil off your desk. Half a second or so. Roughly. But more like my desk, not like your desks. Your desks are about 0.74 up, and my desk's a little taller, so. I should write in your homework now. That's it. Just going to write in the homework, unless anyone has very important questions to ask. Hearing none,